And we are on to number 3. So we're first asked to correct these deformation mechanism maps. So what we're going to do to make our life a little bit easier, I'm going to label different color. So 1 is going to be our theoretical strength, theoretical shear stress. 2 is going to be dislocation glide. 3 is going to be our power law creep. 4 is going to be our elastic regime. 5 is going to be cobalt creep, and 6 is going to be NH. So we're going to have 1, 1, 1, dislocation glide, 2, 2, 2, elasticity, 4, 4, 4, PLC, 3, 3, 3, cobalt creep. We're going to do this. This is going to be 5, nothing here, 5, and Navarro herring is going to be 6, 6, and 6. There we go. Excellent. Let's zoom out. Correct it. Explain the scaling for each creep regime and when they will dominate. So theoretical shear stress, dislocation glide, elasticity. Again, we've already kind of covered those in depth. And we know, so if we want to look at the scaling, we know that in general, our strain rate for creep is going to be some constant of our creep times basically stress. Let's do stress to the x power. Let's do gg to the y power. And then we have d naught exponential minus q times z all over kt. So we know for our PLC, our cobalt creep, and our NH what those values are. So x, y, z. So PLC, we're going to scale here 4 to 6. We are going to do to the y 0, and z, it's going to be our bulk. For our cobalt creep, this is going to be 1. For our herring, 1. Cobalt creep is minus 3, minus 2. This is grain boundary, and this is bulk. Excellent. So now we can get to the next part of this problem. So we've got the correct deformation mechanism maps. Now we can look at, these are all actually maps of the same material that has been annealed for different times and temperatures. So sketch the stress strain curves. So let's go ahead and let's draw them out. So let's go ahead and look. Don't worry about, I am already all vaccinated, so, and boosted, so I can relax. All right, so stress strain curves. So we're going to label those 3 materials, A, B, and C. So again, I'm going to use my old, this is going to be my red, this is going to be my green, this is going to be my blue. So same material that has been annealed at different times and temperatures for each map and describe their corresponding annealing times. So we know that our, basically, you can see here clearly that sigma y of A is the lowest, is less than my sigma y blue, or of C, and is less than my sigma y, less than sigma y of my B, my green. So if they all have the same material, they're all going to have the same slope, but then they're just going to have different yield strengths. So here and then here. So red will be annealed at the longest time, and you can kind of see, or actually, no, excuse me. Excuse me. Yeah, that's not cobalt creep, that's PLC. So red doesn't even have a cobalt creep region, so that will be annealed at the longest time and highest temperatures. So there's 2 strengthening mechanisms that are occurring here. So obviously if we are annealing, we are changing 2 things. We're changing our work hardening, our density of dislocations. So as we anneal, we decrease the density of dislocations, and additionally, our grain size. As we anneal, we increase our grain size. So those are the 2 strengthening mechanisms that are occurring. Consider now the same material, but as solute strengthened, now draw the stress strain curves for each materials. Do you agree with the deformation mechanism map still? How might they change? Describe. So if these are different materials now, so these are different materials, so I'm going to do sigma and E. They might have different, actually they will potentially have different, Young's moduli. So, but the key thing is that you still have that same, trend. So, but this could be, slightly different. And again, the slopes could change, they could be different, but the yield strength must be the same. So slopes are different. Potentially, I'm not sure which is, steeper or less stiff, but again, these yield strength values are the same. So if it's solute strengthened, I do disagree with the strength, it's basically, if you're assuming that they're the same material at the same grain size, then these maps don't make sense. Because here, we're clearly seeing a change in the cobalt creep region, you know, this value here. So we're seeing a change in these, in the, basically the size of this region, and it's completely gone here. So these maps are showing different grain sizes as well. So there's clearly a change in grain size. If you were to solute strengthen, you would probably still change the grain size slightly because you're adding those solutes, but again, you know, that would be the value there. And again, you would just see those changes, and actually they'd be more consistent, essentially. So you wouldn't see that large, huge change in the cobalt creep regions. So that's it. And now we get on to the last problem. Thanks. Bye.